I'm Patrick Lee. Today I'm going to present the work ELAT, enabling erasure coding tiering for LSM-tree-based storage. This is joint work with my students and also my former students and postdocs. So here we consider storage tiering scenario to balance the trade-off between access performance and storage overhead, and also the storage persistence. So we have two tiers here. One is the hot tier. It can provide the high performance, but there will be limited storage space. While at the cold tier, it provides abundant storage space, but there's limited performance. There are many scenarios for this type of storage tiering. One is in the content delivery networks, CDN, where you can treat the CDN as the hot tier and the web service as the cold tier. While, like for example, for the Amazon case, we can use EBS for the hot tier and also S3 as the cold tier. And there are many use cases for storage tiering, and a primary use case for storage tiering considered in this work is edge cloud storage. And our observation is that IoT applications will generate a lot of data. And so what we want to do is we will want to put the hot data in edge storage to process the data. For example, we want to support edge analytics, while for the other types of data, you don't need to access that very often, but you still want to provide the persistence. We'll put this data in cloud storage. And edge storage is, there are many examples for edge storage, but they're mainly built on distributed key value stores for high performance. So our goal here in this work is, can we extend a distributed key value stores with storage tiering to support edge cloud storage, or in general tier storage environments? In this work, we use Cassandra to design this distributed tier key value store. And Cassandra is used in is also cited in the literature to support edge storage. And it has some nice features. It's decentralized. It can support high performance, and it is also fault tolerant. So the idea of Cassandra is we will arrange the nodes in a hash ring. And the key value pairs will be mapped to one of the nodes based on consistent hashing. And we also will generate replicas for the key value pairs. And these replicas will be distributed along the clockwise directions on the hash ring to different nodes. So for example, in here, we have three-way replication. So there will be 3 replicas for each key value pairs. If you look at this example here, we also can see that each node will store 1 replica originating from itself, and also 2 other replicas from the other nodes. So in general, if you have R replicas, each node will store R replicas from itself or maybe from other nodes. Redundancy is necessary in here because edge nodes are in general error prone. So if you lose the data in one edge node, you can recover the data from the other edge nodes without going to the cloud to retrieve the data because of the high edge to cloud latency. Internally, in each node, the data will be managed based on LSM-tree. So the idea is the key values pairs will be first stored in the memory, and then they will be flushed to the disk in a log structure manners. And we call this the access tables. And these access tables will be flushed from the lower levels to the higher levels via compression. So here we use replication to provide fault tolerance. The drawback is replication has high storage overhead. And the thing is, edge nodes have limited resources, so there will be huge storage overhead to maintain the replicas in the edge nodes. So here we consider erasure coding, and in particular we consider NK resolving codes. And so the idea is we encode K data chunks into N-K parity chunks. And the collection of N data and parity chunks is called a coding group. And we will distribute these chunks to N nodes. And so here the redundancy will be N over K, and such that any K of these N chunks can recover the lost data. So compared with replication, erasure coding is shown to save significantly the storage overhead, but the drawback is it will incur high performance overhead, particularly in degraded read and also full node recovery. this is not, the performance issue is not a problem in replication because when you have failures, you can directly go to the other replica to retrieve the data. So the question we want to ask here is, can we still achieve storage efficiency via erasure coding, but at the same time, we can preserve the high performance in tier storage settings? And our observation is that in practical key value storage workloads, there will be a skewed access patterns. So in here, we conduct a simple study on a 10-node Cassandra cluster where we load 100 million 1 kilobytes KV pairs and issue 1 million reads in a Scythian access pattern. So we observed that actually there will be up to L4, and most of the access tables are stored in L4, the last level, the highest level in the LSM tree, but they only have 10% of the access. So that means that most of the access tables in the lower levels will be accessed, while in the last level, there will be a lot of access tables, but they will not be frequently accessed. And if we look into the access tables in the last level, L4, only a subset of them will be accessed. So this means that we also need to selectively look into the access tables that are not frequently accessed in order to apply erasure coding. So based on this observation, this is our contributions. We designed ELAT. This is a distributed LSM-tree-based key value store that enables erasure coding tiering. And the idea is we will replicate the hot key value pairs and erasure code key value pairs in the hot tier so that it can support hybrid redundancy. And also, we selectively offload the cold key value pairs to the cold tier for further hot tier storage savings. ELAT is based on a few key design techniques: LSM-tree-based redundancy transitioning, hotness-aware redundancy transitioning and cold data offloading, and also a tunable configuration mechanism to balance the trade-off between storage and performance. I will explain them in a moment. And our evaluation results show that we can reduce the storage overhead in the hot tier by 56.1% and also maintain similar read-write performance in the normal mode without failures. When we design ELAT, we pose 5 questions here. At what granularity should key value pairs be encoded, and should we apply erasure coding on or off the right path? And we know that the access patterns are skewed, so the question here is how should we consider these skewed access patterns, and also how should we mitigate the access overhead in the code here, and particularly in the edge cloud storage, there will be high latency between the edge and the cloud, so we want to mitigate the access to the code here. And also, how should we balance the trade-off between storage savings and also access performance? So in our design, we extend Cassandra with different design components. So the idea is we will first apply redundancy transitioning in the last LSM tree level. And also, we will offload some of the data to the cloud storage. And in the distribution layer, we apply the tunable configuration of storage performance trade-off. So let's try to answer each of the design questions. First of all, how should we encode the key value pairs? It's not a good idea to encode key value pairs individually because usually the key value pairs are very small, so there will be high metadata overhead to maintain the erasure coding information. So our design here is to apply cross-encoding at the access table levels. And these access tables, we only encode the access tables in the last LSM tree. And so what we do is, first thing we do is we apply decoupled replication management to the LSM tree, which is proposed in our previous work depart, and also in one other previous work tabs by other authors. And so the idea is, remember that each node will store R replicas. Originally, these replicas will be all stored in the single LSM tree. So it's very difficult to separate the primary replica originating from the node and also secondary replicas from the other nodes. So what we want to do here is we separate these R replicas into LSM trees. And one LSM tree is called a primary LSM tree, which contains the replicas originating from the node itself, and also R-1 secondary LSM trees to store the secondary replicas from the other nodes. This design will help us remove the secondary replicas later on, and also there will be some performance improvement as we're going to see in the evaluation. The second question we want to answer is how should we perform erasure coding? Should we do this on the right path or should we do this off the right path? And our design choice here is to apply erasure coding offline. And the reason is that we still want to keep the data in replication form because they will be accessed when they are first being stored. So what we do is we still apply replication through replication, just like in Cassandra, but later on we will select the access table and in the last LSM tree level to perform the encoding. Now when we perform the encoding, one question we need to ask is how do we select the parity nodes? So it's very important to maintain low balancing for the parity access tables. We want these parity access tables to be evenly distributed across the nodes. And at the same time, we don't want to select the nodes that already store the data access tables in the same coding groups. We need to store the parity access tables in the other nodes so that we can maintain the fault tolerance. But we have to achieve these design goals based on decentralized decisions because there's no centralized entity to help us do the coordination. So how do we maintain low balancing, fault tolerance, and also decentralized features in our placement decisions? And here we design a decentralized parity node selection. So basically the idea is we allow each node to select the n-k parity nodes in a decentralized manners. And in our paper, we show that it is possible that if each node performs the decision in the same way, we can achieve low balancing and also the fault tolerance features. So let's say we now can identify the parity nodes. We will select the first parity node as the leader parity node. This leader parity node will be responsible to collect the k data access tables and then apply encoding to m parity access tables and send these m parity access tables to the other nodes. And also, after doing the encoding, the primary LSM tree will also specify the key list and send to the other nodes in the replication group to indicate the replicas to be removed. One subtlety here is that when you try to remove the replicas, the LSM tree may be undergoing compassion. So we have to make sure that the removal of the replicas will not disturb the compassion operations. And again, the details are described in the paper, how we do that. The third question we want to ask is how to take into account the skewed access patterns. So we incorporate hotness awareness into redundancy transitioning. So the idea is we look at the last level access tables, we sort them by the access frequencies and select those with low access frequencies to perform redundancy transitioning and data offloading. And in addition, we will only offload the parity access tables with long lifetime and also offload the data access tables with low access frequency and long lifetime to the code tier if necessary. However, if you want to identify the hot and cold data, and probably you need to define a threshold. Now the question here is how do we pick this right threshold? Because from the user's perspective, it's very difficult to specify the right threshold to achieve the good balance between access performance and storage savings. So in here, what we do is we introduce a tunable mechanism, and the key idea is that the threshold is defined from a user's perspective. So what we do is the user will specify a storage saving target alpha, and in order to control the redundancy transitioning and code data offloading. So for example, let's say the users want to achieve 60% of the saving. So in this case, alpha will be set to 0.6, And ELAT will try to use this target as a goal to try to control what access tables and how many access tables will be encoded and offloaded. And here we will divide the access tables to be encoded and offloaded in 3 cases. The first case is we will apply redundancy transitioning. We will still keep the access tables in the hot tier, but we will convert the last access tables, last level access tables into erasure coding. Now let's say the alpha still is not met. We still can save more. We still want to save more storage. Then we go to the second case. We offload the parity access tables. And the reason for offloading parity access tables is that they are usually only used for recovery rather than in the normal access. So we choose to offload them first. Now let's say if alpha is still not met, and what we do is we start to offload the data access tables with low access frequency. So in this case, we try to meet the storage target in a step-by-step manner. We conduct experiments and on Alibaba Cloud. And so here we specify 12 instances as the edge nodes, and also Alibaba Object Storage as the in other region as the code here. So edge to S has low latency, while edge to cloud has high latency. And we use YCSB as the benchmarking tool. And by default, we consider 3-way replication, 6-4 encoding, and alpha is 0.6. And also we set the consistency levels for write and read as 0 and 1 respectively. And we mainly compare ELAT with Cassandra 4.1, and we run our experiments 5 times, but we also take the 95% confidence intervals under students' t-distribution. And our main results is that ELAT can save storage overhead of Cassandra, but maintain the high performance in normal mode. So let's take a look at some of the results here. The first result is we apply YCSB called workloads, and what we observed is that in the edge storage, we can save 56.1% of storage. And if we also consider the storage overhead in the code tier as well, altogether there will be 39.1% of overall storage savings. And ELAT will outperform, will maintain comparable performance in most of the workloads, but we observe that in the workload E, which is scan intensive, it can achieve a high performance gain. And this is not intuitive, but we looked into that, and the main reason is that we separate the LSM tree into multiple LSM trees, so we reduce the size of the LSM tree, and so the compression overhead is reduced. But I would like to point out that this is really specific for our environment, because we later on run our experiments on Chameleon Cloud for artifact evaluation, and we find that this improvement almost disappears. And the main reason is that Chameleon Cloud has much higher storage throughput and much better higher bandwidth, so we don't see the saving from decoupled replication management. But the point we want to make here is that we can use ELAT to reduce the storage overhead, but maintain almost the same performance in normal mode. We can also consider different key value operations. As expected, ELAT will maintain the performance in normal mode, but will introduce high latency in RISC integrated mode, because you need to go to the cloud to retrieve the data. But the thing is, on Chameleon Cloud, this overhead is reduced from 5 times to 1.2 times. So it really depends on the networks between the edge and the cloud. We also apply the performance breakdown. And the thing is, ELAT will introduce transitioning and offloading overhead in here. But the thing is, these steps will be done offline. So they actually will introduce limited overhead to the normal operations. And again, from our experiments earlier, we see that ELAT can maintain the right performance as Cassandra. We also conduct evaluation on full node recovery. ELAT will introduce 50% higher recovery time, mainly because we need to retrieve the data and parity access tables to decode the lost access tables in primary LSM tree. And the performance is mainly network bound. We also study the impact of alpha. We can show that alpha can actually is effective to quantify the storage saving, and it can basically reduce the storage overhead by 9.2 to 86% based on alpha. And alpha, remember that it specified the storage saving target, and the actual saving is very close, but there's still 4% difference, mainly because when we use alpha to model how many access tables to be offloaded, we did not consider metadata. But we actually measure the performance storage overhead. We also need to consider metadata overhead. So that's why there will be small difference in here. But we observed that for read latency in normal mode, we can still maintain this when alpha is less than or equal to 0.6. We also consider different consistency mode by tuning the read consistency level, and also we generate a number of simulated clients up to 256, and again, the performance is not much difference. And we also have more results in the paper, including resource utilization, the size of impact of key value size, and also coding parameters. To conclude, we propose elect here. The main design features of elect is LSM-tree-based redundancy transitioning with decentralized parity node selection, hotness-aware redundancy transitioning and code data offloading, and also a tunable configuration mechanism for balancing storage and performance overhead. So we published our source code, and we also got the badges, and we can reproduce the experiments on Chameleon Cloud, and I'm happy to take questions and comments. Thank you.